Hello everyone, my name is Hongfei Xue. I'm very glad to introduce our work, mmMesh towards 3D real-time dynamic human mesh constructing using millimeter wave. This is a joint work with my lab mates, collaborators, and advisors from City University of New York at Buffalo, University of Georgia, University of Virginia, and Purdue University. As we know, in the comics, the Superman can see through the walls using his X-ray eyes, but is it achievable in the real world? In this paper, we propose our mmMesh system, the first real-time 3D human mesh estimation system using commercial mmWave radar, which can also help us to see through the obstacles. For existing work, thus far, the most remarkable achievement in this effort is the construction of human skeletons. The existing work includes iPose, iPose 3D, person in Wi-Fi, and Y-pose. However, in this paper, we attempt to construct 3D human mesh from the IF signals instead of human skeleton, because even though the skeleton can provide pose information of the subject, it lacks shape and gender information of the subject to reconstruct a realistic human. For example, the human mesh can enable a more realistic AR and VR applications by capturing the player's body shape and pose. The only work which constructs the 3D human mesh using IF signal is IF avatar. However, our mmMesh system have the following three advantages. First, our proposed system can accurately estimate the human mesh by using only a commercial device instead of a specialized testbed. Second, our system is able to directly estimate the dynamic human mesh in a real-time manner. Third, our model is more extendable since it can be deployed on any devices that can generate 3D point clouds like Kinect, LiDAR, and depth camera. So our mmMesh system can enable a new generation of applications by supporting more sophisticated interactions between humans and their physical surroundings. These applications include the smart home, virtual reality, elderly monitoring, fire rescue, gesture control, and no checkout shopping. To achieve our goal, we need to tackle the following challenges. The first challenge is the sparsity of the point cloud. Due to the limited numbers of antennas on the commercial mmWave radar, the generated point cloud in each frame is too sparse to accurately estimate such a complex 3D human mesh. Our solution is to encode a 3D human body model as a strong constraint, which allows us to use fewer parameters to represent the whole 3D human mesh. The second challenge is to correctly associate each 3D point in the point cloud with the corresponding body segment, since the points from the ambient can be mistakenly regarded as a point from a subject, and the obtained point locations can be inaccurate. Our solution is to incorporate a novel anchor point module to elevate the influence of ambient points and learn the local structure of the point cloud to obtain the detailed body segment information. The last challenge is the specularity of the IF signals. In some frame, the point related to a specific body segment may be absent due to the specularity of the IF signal reflection. Our solution is to use RNN to infer the missing body part from the information of the previous frames. Next, let's have an overview of the proposed mmMesh. During the data collection process, the commercial mmWave radar emits FMCW signals and captures the reflected signals. Then the radar hardware can mix the received signals with the transmitted signals to obtain IF signals. Then we conduct multiple pre-processing steps, and we can obtain the point cloud from the radar. The next step is to construct the 3D human mesh by feeding the point cloud in each frame into our deep model. We can output a realistic dynamic human mesh. Note that in our system, the whole inference procedure can be processed in real time with a latency of 0.3 seconds. In addition, for the training of our model, we use a vacant motion capture system to obtain high precision dynamic pose information of the subject. Based on the pose, shape, gender, and the location information of the subject, we can generate the ground truth mesh to supervise the training of our model. Next, let's look at our proposed deep model. Basically, the model is composed of 4 modules. First, by taking all the points in a frame as input, the base module extracts a representation for each point. The second module is a global module. In this module, the feature of each point is further extracted. Then we use the attention mechanism to selectively aggregate these features instead of the commonly used max pooling operation to avoid unnecessary information loss. Then we fill the aggregated representations with the information from the previous frames by an LSTM block and obtain the global representation GT. To accurately construct the human mesh, we propose a novel anchor point module to characterize the fine-grained local structure of the point cloud, while reducing the impact of noise from the ambient point. To achieve this, we first proposed to dynamically choose some virtual locations near the subject as anchor points, and use anchor points as the grouping center to aggregate the feature of nearby local points. Next, I will explain how we can deliberately choose these anchor points using APG block. First, we define an anchor point template at the origin. The template is like a bounding box, but it's composed of a 3D cubic lattice. We can assume the convex hull of the template is large enough to cover the subject. Then, at each time t, we predict the displacement of the template based on the global representation GT and move the template from the origin to the desired location. Having the dynamic template, we can group the local points near the subject to learn the local structure of the point cloud without concerning about the influence of the ambient point. As you can see in the figure, for each anchor point, we group several points around them and conduct both MLP operation and attention aggregation on each group. As a result, we obtained a vector representation for each group. Since the anchor points are arranged as a 3D lattice in the cube, we can regard all the anchor points representation vectors as a 4D tensor. So the 3D CNN can be used to aggregate these vectors. Then we add another LSTM block to fill the information from the previous frame and obtain the local representation AT. The last module is the SMPL module. We concatenate GT and AT and feed it into a fully connected neural network to generate all the parameters to build a 3D mesh. Then, by feeding these parameters in the SMPL model, we can build a realistic 3D human mesh. Lastly, there are many 5 losses to guide the accuracy of template displacements, subject shapes, subject genders, skeletal joints locations, and mesh vertices locations. Next, I will introduce our experiments. As shown in the image, this is our experimental scenario. In the data collection, we use vacant motion capture system to collect the ground truth pose of the subject. We use commercial TI AWR 1843 boost as our wave radar and use video avatar model to generate the ground truth shape of the subject. For data collection, we totally employ 20 volunteers and ask them to conduct 8 activities as shown in the video. Then let's first have a look at the qualitative result for the basic scenarios. As we can see in the figure, row A to row C shows 3 male subjects conducting different activities. Row D to row F shows 3 female subjects. Row G to row L show consecutive frames when one subject is conducting activity 2. The first, second, and third columns of these rows show the video frames, ground truth meshes, and the generated meshes. The results show our generated meshes looks realistic, and the shape of the generated human mesh are very similar to the corresponding subjects in the video frames. Besides, the results in the figure also show our model can not only estimate the correct pose of the subject, but also construct smooth pose in consecutive frames. Next, I will report the quantitative results in this video. For baseline, since there's no existing model to reconstruct the dynamic human mesh from point clouds, we design our baselines by removing or replacing the modules in the architecture of our proposed mmMesh model. As for the matrix, V is the average vertex error, which is the average Euclidean distance between the predicted mesh vertices and the ground truth mesh vertices. Similarly, S is the average joint localization error. Q is the average joint rotation error. T and G are localization error and gender prediction accuracy. In table, we can find our mmMesh model achieves the best result. The average vertex error is only 2.47 centimeters. Next, we can find that the performance drops from baseline A to baseline B and from baseline C to baseline D, where the attention mechanism is replaced by the max pooling operation. This is because the point clouds in our scenario are very sparse. Using max pooling operation instead of attention can cause the model insensitive to subtle structures of the point cloud and impair the model performance. We can also find the baseline C are generally better than baseline A and B. It demonstrates that it's very important to learn local structure of the point cloud so as to capture more detailed information about the human body structure. Last, by comparing mmMesh with baseline C, we can find that in our scenario, the proposed anchor point-based sampling method is better than the FPS-based sampling. This is because the anchor point sampling method can dynamically sample the points near the subject and avoid including the noisy points from the ambience. To investigate the influence of the occlusion on the performance of our proposed model, we place barriers of different materials between the subject and the radar as shown in row A to row C. Note that our mmMesh is only trained, on the data from the basic scenario. However, we can see our model can still generate high quality human mesh with accurate pose and shape. Row D shows a dark scenario where the vision-based method usually have poor performance. Row E shows a furnished scenario. These experiments also show the robustness of our model. In order to investigate the influence of environment changing on the performance of our system, we conduct our experiments in various environments, including both indoor and outdoor scenarios. The results in the figure demonstrate the effectiveness of our model in various environments. For the real-time performance, here's a short demo. I highly recommend you to watch the full teaser video for more real-time results. To conclude, first, in this paper, we propose a deep learning framework named mmMesh, which can construct dynamic 3D human mesh in real time using the point cloud generated from mmWave signals. Second, we implement our mmMesh system using Quartz mmWave radar. Third, we evaluated our system in various environments and demonstrated its effectiveness and robustness. Thank you.